In this pre-calculus algebra video, we're going to talk about modeling with quadratic functions. So I'd like to point out that first, we often do two things. For all the modeling we're going to do, we're going to be multiplying linear functions together to get a quadratic function. And we're also going to be looking for places where the quadratic function is maximized or minimized. That's very common in applications. Let's see a couple of examples. So first, Stephanie has 600 feet of fencing to fence in a rectangular horse corral. Okay, so Stephanie's creating a horse corral in the shape of a rectangle. And we want to find a function that models the area of the corral in terms of the width of the corral. So I drew two possible corrals here. So in both cases, she used 600 feet of fencing. So we don't know ahead of time what her corral looks like, but we know it's the shape of a rectangle. Okay, so we want to reference the width of the corral, right? So we're looking for a function that models the area. So this will be the width of the corral. Let's call that x. Now let's call this length, that is the length of the corral, let's call that y. Well, what do we know? We know that because this is a rectangle, this is length x as well, and that would be length y. Now we're given that she uses 600 feet of fencing. So if you add up all those lengths together, that is the perimeter, you get 600. So the perimeter, of course, of a rectangle is 2x because you have two sides of length x, and 2y because you have two sides of length y. So we know the perimeter of a rectangle is 2x plus 2y, and because Stephanie uses 600 feet of fencing, the perimeter has got to be 600. So if we take this equation and we divide both sides by 2, we end up with x plus y is equal to 300. And what that does is that gives us a relationship between x and y. If we want everything in terms of the width of the corral, in terms of x, we're going to express y in terms of x. So y is going to be 300 take away x. Okay? So instead of y, we can call that just 300 take away x. Now, we're after the area, right? So what's the area of the rectangle? Well, it's simply the width times the length. So the area is x times y. Now we want that in terms of x. So we're going to replace the y with the 300 minus x. So the area is equal to x times 300 take away x. Now there is a restriction here. And the restriction is that, well, first of all, x of course has to be positive. But notice that x can't exceed 300. Why? Because if it was 300 here and 300 there, that would use up all 600 feet of fencing. So the restriction is that x has got to be positive, but also less than or equal to 300, so that the problem makes sense. So this is our function, and people often write it in function notation. That is a of x is equal to, and if you distribute the x, it's 300x take away x squared. Okay, so this is our answer for part A. This is our area function in terms of the width x. Now you might be asking, well, how should she make the rectangle so that the area is maximized, right? So that the horses have the most space. And that's the question we're going to answer next. So for the same problem, what's the width that gives the maximum area? So we're going to maximize this function. So find the dimensions of the rectangle that maximize the area of the corral. So Stephanie can build her rectangle with whatever width she wants, as long as it's less than 300. And the area function that she's going to be using, as we just talked about, was 300, let's see, what was that again? It was 300x take away x squared. So it's 300x take away x squared. Okay, so we want the maximum of we want to maximize this area. Now this, if you were to graph this, this would be a parabola, because I see there's x squared, but a parabola opening down. And we know that the vertex of the parabola, so if you have a parabola opening down, right, we know that the vertex tells you where you have a maximum. And so what we're going to do is we're going to find the vertex of this parabola, and that tells us where the area is going to be maximized. So the vertex, remember there's a formula for that, and that would be x is equal to negative b over 2a. So when x takes on this value, that's when this area is going to be maximized. So let's see, x is equal to negative b would be 300, and then over 2 times a, and a is negative 1 here. So we're looking at the negatives are going to cancel, and you have 300 over 200, which is 150. And so what that means is that when the width, remember x is the width, when the width is 150 feet, the area is maximized. Now if the width is 150, don't forget the y, that was 300, take away x. So if x is 150, that means y is equal to 300 take away 150. So y, that is the length, is 150 as well. So the length is 150. What that means is that Stephanie would be creating a square, right? Because a square is a rectangle where the width and the length are equal to each other. So what's special about this? Well, it's the maximum, it's where the area is maximized. So if Stephanie wants to use her 600 feet of fencing such that the horses have the most room, she creates a square with her fencing. Okay, let's see another example of modeling using quadratic functions. Okay, so this is a long problem. So a team, baseball team, whatever, plays in a stadium that holds 55,000 people. When the ticket price is $12, the average attendance has recently been 28,000 people. And they had a survey done, and the survey indicates that every time the ticket price drops by $1, every time for every dollar the ticket price is lowered, the attendance increases by 2,000. Okay, so if you drop the ticket down to the price down to $11, for example, the attendance is going to go up by 2,000 to 30,000. And if you make the ticket price $10, it's going to go up by 4,000. That's what this is telling us. Okay, we want to find a function that models the revenue in terms of ticket price. And we're going to let x equal the ticket price and r represent the revenue. Okay, the revenue is the money taken in from the sales of tickets, right? So the revenue, which we're denoting as r, is the ticket price, so how much does a ticket cost, multiplied by the number of attendance, people in attendance. So it's going to be multiplied by the attendance. So for example, if the ticket price was $2 and there were 10 people that attended, you'd have revenue of $20 brought in. Okay, so this is going to be our function, our revenue function. Now our ticket price, we're told to let that be represented with an x. So the ticket price is just going to be x. The question is, what is the expression for attendance? So let's write that over here, our attendance. We're just going to work on that. Well, we know that we have, all we're doing is we're lowering the ticket price, right? So we know that we at least have 28,000 people. So the attendance is going to be 28,000 plus the amount that you get from lowering the ticket price. And this says every time you lower the ticket price by $1, you gain 2,000 people. So let me ask you, is the attendance going to be 28,000 plus 2,000? Well, that's only if you've lowered the ticket price by $1. If you lowered the ticket price by $2, you're going to get 4,000. And $3, you're going to get 6,000. So in other words, you have to multiply this by the difference between the current ticket price, which is 12, and the new ticket price. So this is going to be 12 take away x. So let's see if that's right. If the new ticket price is 10, for example, if x was 10, you'd have 12 take away 10, and that would be 2, and 2 times 2,000 would give 4,000, which is the extra people in attendance. And likewise, if your new ticket price was, let's say, $8, well, this tells you that if you drop it by $4, you're going to gain 8,000 people, right? Let's see if that works out. If your ticket price is 8, 12 take away 8 will be 4, and 4 times 2,000 will be 8,000. So this part right here gives you your extra attendance over the 28,000 due to dropping your ticket price. Okay, so the attendance is going to be this whole expression. It's going to be 28,000 plus 2,000 times 12 minus x. And remember, these are being multiplied together. So your revenue is going to be x times, let's simplify this a little bit. Let's do it over here. It's going to be 28,000. If I distribute that, it's going to be 24,000. Take away 2,000x. And so the attendance is going to be 52,000 take away 2000x. So we have to take the x and multiply by all of this, which simplifies to 52,000 take away 2000x. Okay, and then when we distribute the x, our revenue is going to be 52,000x take away 2000x squared. So that's our answer for part A. This is our revenue function in terms of the ticket price. Okay, so let's see if we have a second part to this problem. And we're asked to first find the ticket price at which the revenue is maximized. Okay, and the revenue was 52,000 x take away 2000 x squared. Let me double check to make sure that's right. 52,000x take away 2000x squared. Okay, so now they want to say find the ticket price when the revenue is maximized. So once again, we're trying to maximize this, right? And because the coefficient on the x squared is a negative, this is a parabola opening downward. So again, we're looking for the vertex. So that would be x is equal to, once again, negative b over 2a. So it's going to be negative. Let's see, b is going to be 52,000. And then 2 times a, well, a is negative 2,000. So it's going to be negative 4,000 in the denominator. And so the negatives will cancel, and you'll get, let's see, it's going to be 13. What does that mean? Well, that means that you make the most, if you're in sales for this team, if the ticket price is $13. Now, notice that you don't want to just raise the ticket price too much, because if you do so, your attendance will drop significantly. So 13 is the magic number where you've raised it just enough, and you have enough people in attendance where your revenue is maximized. You'll make the most money with ticket sales if you price the ticket at $13. So part C asks us, at what ticket price is no revenue generated? So in other words, you could potentially raise it too much, and in which case you have no people attending. So if our revenue function is 52,000 x take away 2000x squared, this question here, part C, is asking us, when is the revenue 0? When is this equal to 0? Well, you can go back and say, well, all we have to do is factor this and set it equal to 0. Now, from what we had a moment ago, the factored form, let's go back to the previous page and have this in factored form, or we can just factor it here. So let's just factor it here, and we factor out, let's see, it's going to be a 2,000 and an x. So you factor out 2,000x, and what are you left with? Well, 26,000 take away x, and that's equal to 0. So what it's telling us is that your revenue is, let's see, take that back. This isn't going to be 26,000, it's just going to be 26. So when I factor a 2,000x out from this, I get a 26. Okay, so when you set these equal to 0, the first option is 2000x is equal to 0, and that's when x is 0. And then the other one is when x is equal to 26. Now, what does this mean? Well, it means that if the ticket price is 0, you don't generate any revenue. That's obvious. No ticket sales, no revenue. But the second option is interesting, right? It says that when your ticket price is $26, nobody attends. You've overpriced it. So $26 is going to be when the ticket price, that's too much. You have no revenue generated. And if you graph this parabola opening downward, you're going to find that these are the x-intercepts. So they're the places where the revenue is 0, and they're values of the ticket price for which the revenue is 0. Okay, so that's how you model quadratic functions. And what's important, what we notice in both cases, is that you have the product of linear functions to get your quadratic. Okay, until next time.